Hello everyone. Now we have to start next article and it is angular SHM from chapter number 5 oscillation. We finish linear SHM. Now in similar manner we have to here learn angular SHM. Now what is angular SHM? Basically in linear SHM we consider example of spring and a block is attached to the spring. Similar manner here I consider example of this is a wire and to that wire this is a metallic disc is attached. So this is a disc. Then when we give rotation to this disc in anti-clockwise direction, then restoring torque is developed in clockwise direction. So restoring torque is developed in clockwise direction. It means that this angular displacement anti-clockwise, restoring torque clockwise, and both are proportional. More the angular displacement, more the restoring torque is developed here. So we can write here, so torque directly proportional to angular displacement and both are oppositely directed, so minus sign. Or I can write here a constant C, so where C is a constant and it is called as torque per unit deflection, means this C is torque divided by theta. Similar manner we learn in the linear SHM, force is equal to minus kx. So you know that force and torque they are analogous. Displacement and angular displacement means the linear displacement and angular displacement, they are also analogous. The similar type of formula we get here. So angular SHM you can define here the oscillatory motion. It's a oscillatory motion or SHM in which restoring torque is directly proportional to angular displacement and both are oppositely directed, is called as angular SHM. Now after that angular SHM we have to obtain differential equation of angular SHM. Differential equation of angular SHM. Now what is differential equation? We learn differential equation in linear SHM. In similar manner we have to learn it in angular SHM. So we know that this torque is equal to minus C into theta, equation number 1. Also in chapter 1 we learn one formula of torque, I alpha. This is equation number 2. Now equate these two equations, we get by equation 1 and 2. We can write I alpha is equal to minus C into theta. Now here this I as it is, alpha we can write d omega by dt is equal to minus C into this theta. Now after that, this I as it is, d by dt as it is, instead of omega I can write d theta by dt is equal to minus C into this theta. I can write here I d into this d square, this theta divided by dt square is equal to minus C into theta. So this is the expression. Now I can shift this I to that side, we get d square theta by dt square is equal to minus C by I into theta. So I can shift to this side, so d square theta by dt square plus C upon I into theta is equal to 0. This is expression for, this is a differential equation for angular SHM. This is differential equation of angular SHM. I hope everyone understood this. So if you see this equation and the equation which we learn in this linear SHM, both are the analogous type of equations. Now after this differential equation, next article we have to learn and it is magnet vibrating in uniform magnetic field. So the next article, in that we have to use this formula. Next article. This article is similar to the article which we learn in the simple pendulum. Not exactly similar, but similar kind of we can say. So Next topic is magnet vibrating in uniform magnetic field. Magnet vibrating in uniform magnetic field. ठीक है. Now we consider a magnet of some dipole moment mu. I consider magnet of dipole moment mu vibrating in uniform magnetic field of induction B as shown below. Now let I draw here a bar magnet. So this is a bar magnet. So this is the first pole of the magnet, this is second pole of the magnet, and this is a magnetic field. And then this is N pole, this is S pole. Then on N pole some force is acting, and this force is plus Mb, because pole strength of this is Mb, or I can write F is equal to plus Mb. On this a force is acting and it is minus Mb. F is equal to minus Mb. So both are equal and opposite forces. They form a torque here, or couple. Now here in this equation we can use, here we write torque is equal to minus C into theta, equation number 1. So this formula we already have, this formula we are written. As well as in 11th standard we learn when a magnet is vibrated in uniform magnetic field, it experiences a torque. How much torque it experiences? A torque acting on magnet. So I write first, we know torque acting on magnet in magnetic field, uniform magnetic field is torque is equal to mu B sine theta, equation number 1. In this formula, this mu is the magnetic dipole moment, B is the magnetic field, magnetic induction, sine theta. Now here this theta is the angle with, this is the direction of magnetic field, so this is theta. Now here also, here in this formula we can write this theta is very small. Theta is very small, or we can say that when angular theta is very small, let I write theta is very small, as theta is very small. Hence sine theta nearly equal to theta. Sine theta nearly equal to theta. So we can write torque is equal to mu B theta. As this angular displacement is in clockwise, this torque is in anti-clockwise. So they are oppositely directed. So hence I can write here torque is equal to minus mu B theta, equation number 1. Also we know one formula of the torque. Torque is equal to I alpha. This is equation number 2. So this formula we learn in the chapter number 1. So by 1 and 2, what we write? So I alpha is equal to minus mu B into theta. Now here I can write, I can shift this I to this side and theta to this side. So I can write here alpha by, or I write formula of alpha first. Alpha is equal to mu B theta divided by I. Now here as mu, then B and I. Here in this formula I is a moment of inertia. Mu, B and I are constant. Hence I can write alpha directly proportional to minus theta. Alpha is angular acceleration, theta is angular displacement. When angular acceleration directly proportional to angular displacement and both are oppositely directed, then it is called as angular SHM. Hence it is angular SHM. Motion of this magnet is angular SHM. Then after that, in magnitude, I can write this formula in magnitude. In magnitude, this formula of alpha we can write alpha is equal to mu b theta by I. So this is formula. Now I can transfer this theta to this side. Hence alpha by theta is equal to mu b upon I. So this is the formula. Now this is acceleration per unit displacement. Angular acceleration per unit angular displacement. Hence period is t is equal to 2 pi divided by alpha by theta. So in simple pendulum article also we learn one formula, t is equal to 2 pi divided by under root of acceleration per unit displacement. So only the thing is same formula we are written here. It is angular displacement per unit angular acceleration per unit angular displacement, means alpha by theta in a root. Now here we can write here this alpha by theta is mu b by I. So I can write a formula of t here. T is equal to 2 pi as it is. So I upon mu b. And this is expression for period. This is expression for period of magnet. Magnet is performing angular SHM in this magnetic field, uniform magnetic field, and this is a period of oscillation. This is expression for period of oscillation of magnet. I hope everyone understood this. In this lecture, that's it only. Thank you.